Hey, welcome! Today, we're jumping into the world of polynomials. And I know what you're probably thinking, flashbacks to math class, right? But seriously, polynomials are way more than just equations on a page. They're like a secret code that describes the world around us, from the path of a basketball to how a company grows. So, let's get into it and start cracking that code. You've seen expressions like this a million times. I mean, they're everywhere in math. But what actually makes something like x squared plus 2x a polynomial? What's so special about it? And what story is it trying to tell us? That's exactly what we're about to figure out.
All right, first things first. Before we can do anything cool, we have to learn the basic rules of the language. You know, the grammar of this whole polynomial code. What does it take for an expression to be allowed into the club?
It actually all boils down to one simple, super important rule. For an expression to be a polynomial, the exponents on the variables have to be whole numbers. So we're talking 0, 1, 2, 3, and on. No fractions, no negative numbers allowed as powers. That's it. That is the secret handshake to get in. This slide just makes it crystal clear, doesn't it? Look on the left. Everything's clean, the powers are all whole numbers like 2, 1, and even an invisible 0. But now look at the right side. That square root of t, well, that's really just t to the power of 1/2. That's a fraction, so nope, not a polynomial. And what about 2 over y? That's just a fancy way of writing 2 times y to the power of -1. And since that's a negative exponent, it's out too. This one little rule is the gatekeeper. Okay, awesome. So now we can spot a polynomial out in the wild. The next step? Let's throw one on the operating table and see what it's made of. We're going to learn the names for all its different parts. And here is our specimen for today. Negative x cubed plus 4x squared plus 7x minus 2. Yeah, it looks a little intimidating, but trust me, it's built from really simple individual pieces. So you see those chunks that are separated by the plus and minus signs? Each one of those is called a term. In our example, we've got 4 terms. The negative x cubed, the positive 4x squared, the positive 7x, and that negative 2 on the end. They're just the basic building blocks. Now, let's zoom in on one of those terms. See the number part hanging out in front of the variable? That has a special name. It's the coefficient. All it does is tell you how many of that variable part you have. So for 4x squared, the coefficient is, you guessed it, 4. And this table just lays it all out perfectly. The term 4x squared coefficient is 4. The term 7x coefficient is 7. That number at the end, -2, well, it's its own coefficient. But here's the one you gotta watch out for. That first term, negative x cubed. You don't see a number, right? Whenever that happens, there's an invisible 1 or -1 hiding there. In this case, it's a -1. All right, we know the parts. Now, how do we start to organize these things? Well, just like scientists classify animals, mathematicians classify polynomials. And lucky for us, the system is actually really simple. The single most important way to classify a polynomial is by its degree. And the degree is just the highest exponent you could find anywhere in the expression. I love thinking of it as the polynomial's power level. A higher degree means it's a more complex and powerful expression. So, giving a polynomial its proper name is a simple 2-step process. Seriously, that's it. First, you count up the terms to get its first name, then you find its degree, its power level, and that gives you its family name. Let's see it in action. This table puts it all together so nicely. Let's take the first one, 7x cubed. It's only one term, so its first name is monomial. Its highest power is 3, so its family name is cubic. Put them together, it's a cubic monomial. Next one, x squared plus x. 2 terms, so it's a binomial. Highest power is 2, so its family is quadratic. And check out that third example. The terms are all out of order, but who cares? It has 3 terms, so it's a trinomial, and the highest exponent is still 2, so it's also part of that quadratic family. So we can spot them, we can name them, now we can start to actually do stuff with them. And the most fundamental puzzle you can solve with a polynomial is finding its 0. Let's start with a really easy one. We'll call it p of x, and it's just equal to x minus 2. Nice and simple. So here's the puzzle. Is there a number that we can plug in for x that makes that entire expression just collapse down to 0? What's the magic number? Let's think about it. What if we try plugging in the number 2? If x is 2, we get p of 2 equals 2 minus 2, which gives us
0. Boom! We found it. That's the value that makes our polynomial equal 0.
And that special number we found, it has an official name. It's called a zero of the polynomial. So, to put it formally, we just discovered that the number 2 is a zero of the polynomial x minus 2. It's the specific input that gives you an output of 0. So, okay, finding a 0 is kind of a neat trick. But what's the big deal? Why do mathematicians care so much about this? Well, it turns out that finding a 0 isn't just solving a puzzle. It's like finding a secret key that unlocks something much, much deeper. And here it is. This is the big reveal. It's called the Factor Theorem, and it is an absolute game changer. It says that if you find a number, a, that's a 0 of your polynomial, then you automatically know one of its factors. It's going to be x minus a, every single time. This is so powerful. It means that hunting for zeros is way more than just a math problem. Every 0 you discover literally hands you one of the building blocks, one of the factors of your polynomial. This is the first step you take to break down a big, messy expression into its simple core parts.
Let's see this thing in action with something a bit trickier, like y squared minus 5y plus 6. Now, if you test it, you'll find that if you plug in y equals 2, the whole thing becomes 0. So, because our amazing factor theorem, the second you know that 2 is a 0, you also know with 100% certainty that y minus 2 must be one of its factors. You've just found a key to unlock this expression.
So look at that. We started with some basic grammar rules and ended up with a powerful key that lets us break down complicated math. We've learned the language of polynomials, terms, degrees, zeros, and factors. So the real question now is, where are you going to see this code in action? What stories are polynomials telling you in the world all around you? Thanks for tuning in.